Just 1 second about RISE. Perhaps most of you already know that officially from 1st of September this year, almost all institutes in Sweden are coupled together under one umbrella, Research Institute of Sweden. So no SP, no RISE, no SIX, no Victoria, so all are together. And our group, from where I'm coming from Göteborg, working on sensors and sensor systems, everything which has to do with from principle to prototypes and demonstrators. So now shall we go a little bit further about sensing and energy harvesting? And we heard a lot about the importance of sensors. And nowadays it's not only just as a nice to have, it's a must important, because we need to control, we need to understand, and we need to increase the effectivity. And we've seen lots of examples where sensors are almost everywhere, and not only one or two, but is getting in a big number. And especially in areas where it's not the easiest. For example, if you want to go on environment or water monitoring, or if you have to have on the field to measure the quality of the soil for agriculture, or example for structural health monitoring on an airplane. So the batteries are a very good, or cables, electrical cables are a very good utilization for power, but there are coming more and more examples where you need large amounts, like Ben said, will be not so feasible and will cost a lot to get hundreds of batteries changed. Or if you want to have it in place, not easy to access, for example, for future of cities, when you want to have sensors inside of the walls or on the bridges, for example, for humidity check or for vibrations in the bridges, you can't change the batteries or you can't have cables. However, at this moment, the possibility to not to use battery will be if you have ultra low power sensors and electronics and communication, low data rate and low duty cycle. So if you want to send every second or every milliseconds, will be quite difficult. So one example for this type of application will be to use miniaturized energy harvester sensors. So for example, cables and batteries, now everybody talks about that can bring too much weight. For example, if you want to place all the sensors to check about 5,000 parameters on a airplane maintenance, at this moment our partner GKN uses kilometers of cables, which add lots of weight, which means that they can't get the real data, which is also when they are in fly. So if you put it on a motor hundreds of kilos, in that moment the strain and stress is not the same like without the cables. Or on the car, all these kilos will just make to consume more power or petrol, but also you will have all the electrical interconnects, and when it's a failure, you don't know where exactly. So you'll have to check the whole length of the cable. So it will be very good if all these cables will disappear, or at least will have shorter lengths, which means that the space and the weight dislocated by all these cables could be eventually used for autonomous sensors, in this way increasing the safety of the cars. Or you have application, for example, if you want inside of the motor, and combustion motor or hydraulic motor, if you want to know the parameters of the oil, what is the quality, what is the temperature, what is the pressure, how much water you have, it will be difficult to have a battery, especially because it's liquid, but also can have high temperatures. So everybody knows now, if you have a wireless sensor network or for Internet of Things, you know that you have a power supply, you have a microcontroller, sensors, communication. It was very nice, Michele showing all this. However, in the moment you'll have an energy harvesting, you'll get two components extra, energy converter and energy management, which in principle means an energy storage and power management to convert from the energy source to the supercapacitor or energy storage. What type of energy harvester sources we have for miniaturized applications? So I'm not talking about waves, windmills and everything. We have light, photovoltaics, thermoelectric, the difference in temperature. We have the kinetic vibration or rotation, and we have the RF, radio frequency or inductive. For the kinetic and vibration, here we'll have in principle four types of transducing. We will have the piezoelectricity, we have the magnetic, we will have the capacitive, and we will have the magnetostrictive. As I'm working both at RISE and MIT University with Group Banked, they are working mainly on light and magnetic, and we are working mainly on piezo, a little bit on magnetic and also inductive. So some examples of energy harvesters. Everybody knows the dynamo from the bicycle. It was a very good invention to have your light. Now disappeared. I don't understand why, because you get more exercise. Or the wind up torch. You have it if you want to have. More modern, we have the kinetic from the watches. What is at this moment presently used in application, mainly it's for wireless sensing, for example for the trains, when they need for logistic and tracking the cargoes going, where they are going, and what are eventually the temperature vibrations. And of course the future, we would like to have also the possibility, for example, for implantable devices, not to have a battery inside, like in the case of the pacemaker, such that instead of having the pacemaker and all the wires which can give medical complication, you can have just a small pacemaker with the energy harvester inside, which can take the energy from the movement of the heart or the blood vessel pumping. And for this there are two European projects. One, Smart Memphis, we were working on, and then another one, Manpower, where they are looking how can you use the heart as a source of energy for a pacemaker. What exists commercially, in principle, they are mainly for the electromagnetic or magnetic part. So we have few companies, while for the piezoelectric, unfortunately, it's not so much. They are mainly just the transducer itself, so just a piezoelectric material sandwiched between electrodes, which can bend and create electricity. I assume some of you know about magnetic transduction and piezoelectricity, so I will not go into detail. Our group works with different principles and for different applications, for example, for tire pressures monitoring, sensing, and then we have for the medical to try to see if we can have energy instead of the battery for the pacemaker. We are working with piezoelectric fibers and ceramic PZT, electromagnetic, and also with RFID, which it's already for about 20 years, but can be considered an energy harvesting, because if you use a passive RFID tag, it means that you get the energy from outside. And we are working to have it sensors to monitor on the field, or even, for example, for traceability and recycling of textile, if you have information on it. The work at MIT University Banks Group, they are working on two principles. Here I will present only one, about how to have a self-powered rotation RPM sensor. And they are using the variable reluctance energy harvesting, because if you have rotating material and you have a coil and a permanent magnet, in that moment you can measure, you can use the field, magnetic field created here to measure, to get energy. And so you can make a prototype and test it in the lab, and they build a very good, an exceptional good instrument how to test the harvesting and the sensing. However, you make it in the lab, but when you want to have it in practice, it will be difficult sometimes to get a real hydraulic pump or a combustion motor or something. So how do you test in the lab as close to reality as possible? And this is a very good example of work on which you try to build as close as possible with the reality and how to test it, because for them, for the company, it will be more difficult to stop a production or to have some machines which will be used just for the testing. You cannot open, demount it, or arrange it to test it. So they build an equivalent for the pump, and you have the coils. They have a Bluetooth card, so they can send the data, and we can see the temperature and the angular velocity via Bluetooth data. Now, which are the challenges for these energy harvester systems? In principle, it sounds quite easy. You capture the energy, you store it, and then you use it. The question is, how do you do this? Because if you have an installation like this one, and you want to place, for example, an energy harvesting and electromagnetic, for example, from Revive company, how do you know where to put it? How long you'll... So the design, it's a questionable, or at least at this moment, is not an easy way. And here is the drawing from Sebastian. Thanks for using it. Because when you have a battery or a power supply cable, you know you have so much current, so much volts, and how long will last. However, here, you don't know too much about, are there movements, or do you have enough light if you go on the solar? Do you have enough rotations? Will be there present all the time or from time to time? Which are the parameters you need? The amplitude, the frequency, the positions, because not always where you want to measure or where you can get the energy will be the same place. Sometimes you will need perhaps some wires or some way to transport the energy. Which are the size specifics? They are smaller, they are bigger. Which are the load, the sensor part, the communication. And then you have losses. There are lots of losses in this, all the transaction and all the steps from each step you'll have. So these are the things which people are starting now to work on it theoretically, but also experimentally. You need to gather lots of information, history, such that you can build a database to know, okay, if I want to put it on a hydraulic pump and I know that my pump will work in that factory for so many years, then at least we measure the vibration or the temperatures there, then we know the data. But if I want to move that hydraulic pump in another place, for example, from working outside, inside, outside, then the parameters will change. So at this moment, all this change parameter will make the design of a whole system quite difficult, because to have success in a commercial application, you can't say, this is my harvester, work with it, because you need also the energy storage, you need also the power management, and eventually you need also communication. So it will be good if we can succeed to have the whole system, because only one part is not enough for a company to take it easy in application. Because as we've seen here, each of these can be a bottleneck. So you have to design the whole system in a proper way so that the whole flow works properly. Otherwise, one of these can delay or can consume more. So, as a conclusion, we need the whole system. Only one component is not enough. And we need to work at this moment quite a lot in the power density, such that more applications can be touched and achieved. We need more work on ultra-low power for electronics, communication, and sensors. And most of the applications they need continuous energy. So we need to have also very good storage for the energy in such a way that when we don't have vibrations or rotations or magnetic field, at least we can get it from there. And also on the standardization, it's important, because if each component has its own IPs or has a different way of communication or at least interfacing, then you can't build a nice Lego bit. So as all new technology, there are of course high initial costs if we compare with the batteries. And also at this moment we need, as I said, work in power density. So the micro or miniaturized energy harvester can give quite low power at this moment, but will help at least in the first stage to extend the lifetime of rechargeable batteries, and we will see with the future how much we can replace them. And I said it's no one size fits all. So each application will need at this moment their own energy harvesting system. And will be so people need to know that it's a lot of work still to be done, not only on the design but also on material science, because if you go on piezoelectric, the quality of the piezoelectric material is important. The way it sits on a substrate, the way it's mounted, because if you mount it in a not proper way, perhaps the vibrations which you don't need will be transferred in it, or you don't catch all the vibrations on the unit you place it in. So that one, it's very important to work together with the company to see exactly the locations, application, and what they need. So that was a very short and fast introduction to give you just an idea about what it is, because I can talk many hours about challenges and also the successes in this. Thank you.
Thank you.